Welcome to week 3 of chemistry. In this unit and in this week, what we're going to be looking at is molar mass and how we can use molar mass as a conversion factor. And we're also going to be looking at limiting and excess reactants. So let's go ahead and get right to it. So molar mass is a conversion factor. There's a couple things that we actually covered last week. So let's go ahead and kind of review a couple key ideas. The molar mass is the mass of 1 mole of a compound. And we could find that by taking the individual masses of each type of atom, and we find those masses on the periodic table and we add them together. For example, sodium chloride, NaCl, is composed of 1 sodium atom and 1 chlorine atom. And together, we can get the molar mass for sodium chloride as being 58.443 grams per mole. Now, I went over this last week, and what we can say is that if I wanted to weigh out 1 mole of sodium chloride, it would weigh 58.443 grams. So 1 mole would be that. Now, if I change the compound, it would have a different mass because it's composed of different atoms. So what if we had the mass of 2 moles of sodium chloride? What would that mass be? Well, it would be double the mass of 1 mole because we're doubling the amount of moles, so we're going to have double the mass. So we have 116.886 grams of sodium chloride would be 2 moles. Pretty straightforward, right? So what if we, so what this idea is that we can actually use this conversion factor to convert between grams and moles of a compound or a substance. So what we have is we actually have 2 conversion factors that we can plug in using dimensional analysis. Now, whoops, let me go back. So our first one, we could either have grams on top, 58.443 grams of sodium chloride over 1 mole of sodium chloride, because those 2 things are equivalent. Or we could flip the entire conversion factor and we could have 1 mole of sodium chloride over 58.443 grams of sodium chloride. Now they're going to do different things. That first one, the 58.443 on top, this is going to be converting moles into grams. However, this one right here will allow us to convert grams into moles. So they're going to be converting between different things. So let's go ahead and let's look at a couple different example problems of how we would actually use these conversion factors in a problem.
All right, so we have a couple different questions here that we're going to be working out. So the first one says, what is the mass of 5.65 moles of magnesium chloride? So when we solve this problem, the first thing that we need to realize is that we're going to be converting from moles of something to grams of something. And in order to do that, we're going to be using our molar mass. So we need to be able to calculate the molar mass of magnesium chloride. I'll go ahead and show the work for the first one, but for the other ones, what I'm going to do is I'm just going to assume that you guys know how to calculate your molar mass because we did that last week. So we have magnesium chloride. This is composed of 1 magnesium and 2 chlorine. So if I were to write this out, this would be 1 times the molar mass of magnesium, which is 24.305 grams per mole. Don't forget that. And then this one's going to be 2 times 35.453 grams per mole of chlorine. Now we're going to go ahead and add those together, and what we get is we get our molar mass to be 95.211 grams per mole of magnesium chloride. And last week I talked about this idea that we can rewrite this and we could say 95.211 grams of magnesium chloride is equal to 1 mole of magnesium chloride. So that's kind of going to be helpful when we set up our problem. So when we set up our problem, you always start with what's given. And what's given is that we have 5.65 moles of magnesium chloride. And now I'm going to go ahead and I'm going to plug in my conversion factor so that my units cancel out. Now since I have moles on top, I'm going to put this at the bottom. So it's going to be 1 mole of magnesium chloride. And that's equal to 95.211 grams of magnesium chloride. My units cancel out because they're on opposite sides. And so then what I'm going to do is I'm going to multiply across. So I'm going to put 5.65 multiplied by 95.211. And what I end up getting is 5.37 whoops, excuse me, not 5.37, 537.94 grams of magnesium chloride. So that's how much 5.65 grams of magnesium chloride would weigh. I would have to weigh out 537.94 grams of magnesium chloride. Note that on my calculator, I had more significant digits, but just go ahead and keep 2 after the decimal to make it a little bit easier. So let's go ahead and move on to the next one. The next one says how many moles is 54.7 grams of H2SO4. So again, I'm going to go ahead and assume that you guys can solve for the molar mass. I already solved for the molar mass, and the molar mass for this is 98.078 grams per mole. And in this problem, we're doing the opposite. So in the first problem, we went from moles into grams. Now we're going to be going from grams into moles. Still start with what's given in the problem. So we know we have 54.7 grams of H2SO4. And now what I want to do is I'm going to plug in my conversion factor. Well, I want grams on the bottom, and it is 98.078 grams. And my moles is on top, so it's going to be then 1 mole. And again, remember that my units cancel out because they're on opposite sides. One's on top and one's on the bottom. Now what I'm going to do is I'm going to divide. So I'm going to take my 54.7 and I'm going to divide it by 98.078. And what I end up getting is 0.56 moles of H2SO4. Now, the next problem was a little bit different, and it actually puts together the ideas that we talked about last week and what we talked about this week. So we have a chemical reaction, and the first thing we're going to do is balance it. So here is my reaction. I have hydrogen reacting with chlorine, and it's going to form HCl. So if I take my inventory, I see I have 2 hydrogens, 2 chlorines, 1 and 1. So all I need to do is simply just put a 2 in front of there to balance out my reaction. Now my first part of the problem says how many moles of chlorine are needed to produce 4.56 moles of hydrochloric acid, or HCl. So I'm going from moles of HCl to moles of chlorine. And if we're doing a mole to mole ratio like this, we're going to do what we did last week, where we're going to be using our coefficients to create that mole to mole ratio. So if I were to think about this and I were to think about what the molar ratio is, what I see is that it's 1 mole of chlorine. And remember, it's 1 because there's an imaginary 1, and that's equal to 2 moles of HCl. Now my problem says that I start off with 4.56 moles of HCl. So what that means is that I'm going to put my 2 moles of HCl on the bottom so that those cancel out, and my 1 mole of Cl on top. And when I divide, again, notice that these are on opposite sides, so I'm going to divide. It is going to be 2.28 moles of chlorine. Now what the problem says is it says how many grams of HCl are needed to produce that amount. So now what I'm going to do is I'm going to take my answer that I have here and I'm going to convert this into grams. So I'm going to go from moles into grams. So this was A and B. So B says now how many grams are needed to produce the 4.56 moles of HCl. So I'm going to have 2.28 moles, and I'm going to use my molar mass. So I'm going to use my molar mass, and I already calculated this. So 1 mole of Cl2, and that's 2 chlorine, I'm going to add those together, is 70.906 grams of Cl2. Units cancel out. I'm going to multiply these across, and I'm just going to keep 2 digits after my decimal, and I get 161.4 0.67 grams of Cl2. So notice that we have two conversion factors. So if I have, say, moles of substance X, and I want to convert that back and forth between moles of, say, another substance, we'll say substance Y, well, the first thing that you need is you need a balanced chemical reaction. And once you have a balanced chemical reaction, you're going to use a mole to mole ratio. And that mole to mole ratio is from those coefficients in your balanced chemical reaction. And again, this right here, this was last week's lesson. Now what we did is that we took it a little bit further with one of our ideas. And what we said is, well, okay, what if we have moles of Y? How are we going to convert between grams of Y? And this is going to be, we're going to use the molar mass of Y. And when we do that, we're going to have some number of grams of Y based off of our chemical reaction. I'm going to put Y in quotes so you guys can see the difference between the G and the Y. And that's going to equal 1 mole of Y. So we can use those conversion factors.
What we said last week is we said that balancing a reaction is like a recipe. And I had this recipe of banana bread where we have the amount, the measurement, and the substance. And we add these all together, and we know that from last week that this would make 1 loaf of banana bread. So all these would produce that. Now my question becomes, what if you only had 1/2 a cup of flour? So you only had 1 and 1/2. So you don't have all the flour, but you had everything else. You had every other ingredient in excess. What would that do to your recipe? Well, hopefully what you would see is that flour would limit what you can use. You can't use 1.5 cups of flour and still use the same amount of every other reactant. So what we would see is that flour is going to limit how much bread we can make. It's what we call our limiting reactant. Everything else that we have an abundance of is called our excess reactant. So to get these definitions, what we see is limiting and excess reactant. A limiting reactant is a reactant in a chemical reaction that limits the amount of the product that can be formed. This reaction will stop when all the limiting reactant is consumed. So we don't have enough of our limiting reactant. And once all the limiting reactant is used up, we can no longer continue the chemical reaction. On the other hand, we have excess reactant, and this is a reactant in a chemical reaction that remains when the reaction stops and when the limiting reactant is completely consumed. The excess reactant remains because there's nothing left for it to react with. So if we go back to our previous example and we think about that, every other ingredient was our excess reactant other than the flour. So what that means is that when I'm done mixing all my ingredients together, I have leftovers of everything else, and that is my excess reactant, where flour is limiting how much I have or how much I could create. So what you're going to do is you're going to take a little bit closer look at limiting excess reactants just qualitatively, which means that without calculations, you're going to be taking a little bit closer look at what these limiting and excess reactants might be in the POGL. You also have your homework assignment, which has 2 of the problems similar to the example that we previously did. So make sure you guys get your homework turned in by Friday, and don't forget to do your quiz.